All right, and 72% of you fell into the trap. So let's think about this. Now, this is sort of a little factoid that you actually was in the book in the last chapter. Well, let's talk a little bit more about it now. If you have a sphere, okay, and the sphere is uniformly charged, okay, doesn't matter whether it's a conductor or an insulator. We're just talking about the geometry here. The geometry is uniform charge spread over the entire sphere. The electric field due to that charge inside is equal to 0, right? Okay, that's basically what it's just reminding you there. Okay, the electric field inside a uniformly charged sphere due to those charges. Okay, we're not talking about any other charges elsewhere, but just due to those charges, it all adds up to 0. And we'll actually prove that more formally later in the course. Okay, we just kind of take it as a factoid right now. It essentially has to do with cancellation, right? There's charge on this side making electric field pointing one direction, but that field is canceled by the charge on the other side. Well, if there's 0 electric field and I have a neutral molecule in a region where there's 0 electric field, how's it going to polarize? It's not going to polarize, right? Question. Okay, what if a molecule's not at the center? Well, it is. Okay, it's not at the center, but it says the result is that the electric field basically everywhere inside this sphere is equal to 0. Okay, so even if you're here, or here, or here, or here, or here, if the electric field is 0, then it turns out that there's no polarization. Okay. Now, you might ask, well, what if you get really close to the surface? And then things start to break down a little bit because, as we'll see, and you'll actually have a homework problem on this for next time, we say it's a uniform charge distribution, but when you get down to the atomic level, there may be one atom that has an extra electron or an extra ion here, and then very far away from that on an atomic scale, there's another one with an extra electron. And so what looks smooth and uniform at a distance may at the atomic level be kind of non-uniform, okay? It might be kind of point charges here and there. And so when you're right at the surface, it kind of breaks down. But as long as you get a few atomic diameters away, sort of several nanometers away, you're at a point where that charge distribution looks smooth. The electric field is essentially 0 inside. Polarization is 0, okay? Okay. If it were a metal sphere, for a metal sphere, first of all, can we have induced dipoles in a metal? No, we're talking about a mobile sea of electrons, right? Not electrons that are bound to individual atoms, okay? So even drawing dipoles is a bad idea because we're talking about a conductor, not an insulator. But then again, even in this case, what's the net electric field inside, if this is now a metal? Net electric field is equal to 0. In fact, for the case of a metal, it doesn't even have to be a sphere, right? It could be any old object. The geometry doesn't matter. And no matter what you have, if you have a metal at static equilibrium, the net electric field inside has got to be equal to 0, okay? So this is sort of a geometric property of adding up all the electric fields due to all the charges, and you get this result, which we'll prove later. Has nothing to do with whether it's conductor or insulator. Okay, when you have a conductor, no matter what the charge distribution is, no matter what the shape of the object is, when you're at static equilibrium, net electric field's got to be equal to 0.